and welcome to Prescriptive Analytics. In this lecture, we're going to talk about transshipment models. My name is Hari Rajgopalan and I will be your lecturer for this video. So transshipment problems contain both supply nodes, demand nodes, and then the third set of nodes called transshipment nodes. And so let's take an example. We have BMC, which manufactures luxury cars in Hamburg, Germany, and exports cars to sell in the United States. The exported cars are shipped from Hamburg to ports in New York and Jacksonville, Florida. And then from there, you are transporting it to Boston, Massachusetts, Columbus, Ohio, Atlanta, Georgia, and so on. So currently there are 200 cars available in New York and 300 in Jacksonville. And here are the cars needed in Boston, Columbus, Atlanta, Richmond, and Mobile. And they want to find the least costly way of transporting these cars from the ports to the cities that they are needed. So here's the table that shows the possible shipping routes available. So we have New York to Boston is $40 per car, and New York to Richmond and so on. And here's the supply given here. And of course, you could probably add the demand underneath here on this. Oh, here's the demand here, 160. Here's the demand for each of these cities. So we're going to look at this as a math model. So let's think through this problem. So here we have if you look at this here, so we can go from New York to Boston and Richmond. And then from Boston, you can send cars to Columbus, but you got to keep 100 cars. So let's assume that you send 200 cars to Boston. You got to keep the 100 cars in Boston and then send the rest to Columbus. From Columbus, you can send it to Atlanta, but you need to keep 60 cars. Richmond, I assume Richmond only receives cars, doesn't send anything anywhere. Atlanta, because Richmond gets it from New York. Atlanta can send to Richmond and Mobile, but needs 170 cars. Mobile, can send to Atlanta, but needs 70 cars. And Jacksonville can send to Richmond, Atlanta, and Mobile, and supply is 300. So some of these, like Boston, are both supply and demand nodes. They're called transshipment nodes. Richmond, on the hand, is a pure demand node, whereas New York and Jacksonville are supply nodes. So that's pretty much how we look at the problem. Also, if you calculate our number of cars is about 500, and then the demand here is about, let's calculate 150, 250, 310, 380, 480. So supply is more than your demand. And so let's visualize this problem. We have New York, 200 cars, and you can send it to Boston or Richmond. It goes to Columbus, Atlanta. Atlanta can go back to Columbus and Richmond. Goes to Mobile too. Mobile back to Atlanta. And Jacksonville sends it to Richmond, and so on. Okay. So transshipment problems, for each arc, the decision variable is of course xij, from node I to node j, amount being shipped. So example, x12 is the number of cars going from New York to Boston, x56 from Atlanta to Mobile, and so on. So total supply is 500, total demand is 480. Total supply is greater than total demand. So we can send as much as we want. We can satisfy all the demand. So minimizing total shipment cost is, as usual, we are taking each one of these. These are called arcs, these arrows. This is the supply point. So $30 per car, x12 is the number of cars we send from 1 to 2, right? So here we go. So that's basically the total cost here. And then we've got to look at each node, right? So node 1, we are only sending things out, x12, and node 1 to 2, 1 to 4 is less than 200. Node 2 you're going to be receiving and sending stuff. So what you're receiving is 1, 2. What you're sending out is 2, 3. So this minus this 100 remains. You got to keep 100 back. Similarly, node 3, you're receiving 2, 3, and 5 from 5, 3, but you're also sending to 3, 5, and what's remaining is 60. And you can go on doing each node until you get to the end. And your non-negativity constraints, of course, are greater than 0. So 1 and 7 are supply nodes, and you can see that 2, 3, 5, and 6 are transshipment nodes. 4 is a pure demand node. So let's look at this in Excel, and then we can talk about the optimal solution. So here is the Excel file and how it's set up. Here is the model. And as you can see, we have set up all the variables on top, your decision variables, your objective coefficient, put your sum product, and then you set up the rest, your constraint coefficients, left-hand side formula using sum product, right-hand side numbers, and you can set up the problem and run it. Okay, so this is pretty simple to set up, easy to do, and as you all know, there is another custom setup which I'll show you in a different problem on how to do a custom setup for transshipment problems. So here's the solution. We are sending 120 and 80 to Richmond and Boston. So there's 20 extra in Boston, and so that 20 goes to Columbus. From Jacksonville, we send 210 and 70 to Atlanta. Atlanta needs 170, so 40 goes to Columbus, and 70 goes to Mobile. So Columbus gets its 60 through that. Now let's look at another transshipment problem, and I'm doing this problem specifically so that I can show you another way of, in transportation, I showed you another form of doing your Excel files, and that's pretty much what I'm going to show you here. So here we have XYZ makes tables from factories 1, 2, 3, and it has a warehouse at 4. They have markets and ABC, and then here we have the supply and demand, which are given. And here we are specifying that 4 and D are the same thing. So warehouse 4, when it's sending stuff out, it's called 4. When it's receiving, it's called D. And there is no cost inside, processing cost inside a warehouse. Otherwise, you can put it here. So D is the intake part of the node. 4 is the outflow. So as you can see here, you can either send from 1, 2, 3 directly to ABC, or you can send it through the warehouse. So decision variable, of course, we're going to use Xij. So 1A is 1 to A, 4C is 4 to C. Total supply is 600. Warehouse capacity is 120. Total demand is 260. You cannot add the warehouse capacity to supply. Okay, so we have 600, 260, more than enough. Supply is definitely greater than demand. So we're going to minimize the total cost of shipping. So you're going to use cost multiplied by each arrow, right? This is the same. Subject to constraints, your supply nodes, as you can see, you don't have to send all of them. So everything going out of 1, 2, and 3, you're going to have less than signs. Your demand nodes will have equal to signs because you're going to meet all the demand at A, B, and C. And the warehouse node, you have to put warehouse capacity. So from anything which is coming from 4 to A, B, and C is less than outflow is less than 120. Or you can kind of do the inflow part where you can kind of say things coming in 1 to D, 2 to D, 3 to D is also less than 120. So one of the two you've got to put it. And then you can say 1D plus 2D plus 3D is equal to 4A, 4B, 4C. Now, because this is an inflow and this is outflow, you've got to assign inflow to outflow. And then you got to have the non-negativity constraints. And of course, you can do this with the normal Excel file, but I'm going to show you a special way of doing it in Excel. And that's pretty much why I have this problem. So let's take a look. So here's the information we have. Here's the model. Here's the information we have. And just like we did, and you'll notice that here this is blank. So just like we did, I'm going to, in transportation, I'm going to go ahead and copy this down. And instead of cost, you're going to say units sent, right? That's what we have here. We have supply is what we are sending, demand is what we are receiving, and these are your decision variables, right? So let's put a different, let's change, this is number. Don't always never forget to either color code and format, so important. So here we are going to do sum, and these will be copied down here, right? And again here, this is sum of these. I made a mistake, so let's fix that. And then they are going to be copied right here, formulas. All right, so now that we have set it up, your total cost is equal to sum product of all your cost per unit, comma, this. Right, this is your total cost. All right, and optimization objective, we want to minimize our total cost, right? So that's this, we want to minimize this, that's right here. Okay, let me go ahead and there we go. Now your variables are these are what you want to send from one place to another, so that's your variables. Your constraints are, of course, here all your supply constraints, what is sent is less than what you, including your warehouse, right? Because you cannot send out of your warehouse more than 120 units. That's your capacity. So the capacity constraints get taken care of. Then here, your demand constraints right here will be equal to these, all right? And I'm going to go ahead and also put total received in a warehouse. And now I'm going to kind of, let me color code this so you understand what I'm doing. The total amount of sent from a warehouse should be equal to the total amount received from a warehouse. So we're going to say add constraints, F13 should be equal to E14. And then you're assuming non-negative is true, and you run it, and you get your answer. So you can do it the rectangular fashion like you normally do, or you can handle it this way. There you go. Right, so you're sending from 1, you're sending 40 to the warehouse, and then from 3, you're sending 80 to the warehouse. And oh, and you also have to constrain this. Now remember, cost here is 0, so you've got to constrain this to be equal to 0. You cannot, right now the numbers come such that it's 0, but since you cannot send anything from 4 to D, you've got to constrain that. Let me rerun it again. The answer is the same in this case, but if you don't put this constraint, that's wrong. So it's important that you do that. And that's basically how you use this setup for the transshipment problem.